Everything's set up. Excuse me. We can get started with the this session 3. Thanks, everyone. I'm sorry you can't see it, but you've got a full house here. The room is full. So the first speaker of the session is Ken Goldberg from University of California at Berkeley. And he'll be talking about deep learning for calibration and control in robot-assisted surgery. And I think some of his colleagues are here as well. Oh, now we're seeing that you are sharing your screen. Hopefully that.
There we go. Sorry.
Okay. All right. Well, thanks, Ken.
Okay, great. Thank you, Peter. Thank you all for being here. And it's a pleasure to present this new work. And I also want to acknowledge that Daniel, Seita, and Brijan are here, and they're online and can answer questions. And please do chime in whenever necessary. And also Minho Wang, we'll mention him as well. He's in Korea right now and he's not able to join us. So what we're going to talk about just in approximately 15, 16 minutes, we have some time for questions, is two new topics, which is peg transfer and needle transfer that we've been focusing on, and we have some new results over the past 6 months. So let's start with peg transfer. And I believe everyone here is very familiar with this standard fundamentals of laparoscopic surgery task, which is using rigid objects, moving them from, we call them blocks, between different pegs. And so the challenge in doing this in an autonomous fashion is the inaccuracy of the robot. And again, I think everyone here is very familiar with this. The Da Vinci is the one we use, and the DVRK, and the accuracy has always been a challenge. And when we did some studies of this, we found the errors were up to 5 millimeters in terms of repeatability. Then the second is perception, which can be challenging. And in this case, we colored the pegs and blocks both red to be a little more realistic to surgery, and so you have some challenges for perceiving where they are. And then there is, in past, there have been some really interesting work on this. Jacob Rosen at UCLA and his group have done some work with the Raven on this problem on fully autonomous peg transfer. They got some pretty good results. And one of the other aspects I want to mention is bimanual, which is to use two of the actuators together and use handoffs. So what we've been looking into is, in the last couple of years, is a couple aspects. To address the motion inaccuracy, we have been investigating motion compensation, and I'll talk about what we mean by that. For perception, we've introduced depth sensing. And we realize that that's not currently feasible in real surgical settings, but we wanted to explore what its potential is, and we'll talk more about that. We do want to relax that assumption later. And we've been, in terms of speed, we've been looking at some ways of doing trajectory optimization, and then we want to put this all together. So let me tell you where we are. We fabricated a very precise version of the peg transfer and in the plastic in red so that it would be very consistent. And you can see there's very narrow clearances, approximately 1.5 millimeter clearances between the peg and the blocks, and where you have to reach in and pick them up. And I also want to note that there's been other work in calibration and in manipulation here, and this is just a very small sample, quite a bit of work here. And on the calibration side, the idea that we tested was, could we introduce an artificial fiducials? In this case, there are 3D printed spheres that we colored as well. And the nice thing about these is that there's a rough surface, so they get picked up very easily by the RGBD camera. So we're using a Zivid camera, which is a nice high quality camera. By the way, these RGBD cameras are coming down in cost and increasing in resolution. So they're widely available. And the nice thing is once you have this, then you can actually determine the ground truth pose of the tool very accurately. And then we know what we're commanding it. So we generate lots of these command pose pairs. And so then we try to learn a model to compensate for deviation in the between the command and the final orientation pose of the tool. And this can be done very fast. We generate a very large data set by essentially randomly moving the system around. And here you see that flashing is with the depth camera taking images, and that's in real time. And then we were able to collect, in 18 minutes, about 13,000 or 1,300 data points, and that's for each arm. And then what we identified was interesting, that if you look at the overlay of the measured versus predicted, there's the error in the first three joints of the DVRK is actually very low, but there's error in the wrist. And everyone's known that pretty much, but it was helpful to get that quantified. And what it really came down to was a hysteresis. It depended on the cable windup, and so we started looking at that more carefully. And we thought, what if we look at the sign of the velocity? In other words, what direction are the joints moving in? So we don't need details on the velocity, but just the sign of the velocity. And then we fed that in. So what we did was gave it a set of values and facts, but it turned out that the sign of the velocity was the critical one, where we can train an LSTM neural network to predict the joint angles. And the result of that was quite impressive. We were able to go from three or higher millimeters of error down to 0.65 millimeters. And so we were really I pleasantly surprised. I want to give full credit to Minho Huang, who was a postdoc in our group, who came from Korea. And oh, sorry, is there a question? No. Okay, please interrupt me if there's a question, because I can't see anything except my screen right now, unfortunately.
I think you heard some sound from the room next door. So.
Oh, okay. Good. So Minho is a postdoc, and he's just fantastic. He came in and really analyzed the system so thoroughly and professionally, and really was able to achieve this milestone where he got the precision down to a level which was really it changed my way of thinking about the DVRK. That suddenly it was repeatable and much more accurate than I'd ever believed it possible. So with that, we started to look at could we perform this task autonomously? And so Minho set out to, once he had this calibrated, we were able to actually reach desired points fairly accurately. Using the RGBD sensing, you can see that it's able to determine where the pegs are, the blocks are on each peg, and that allows you to define a desired grip point, and then how to do these transfers. And he also wanted to optimize the entire motion. So as you can see here, there's the motion is, and we'll say more about this in a minute. The other aspect that's that was novel here is that he looked into the trajectory optimization, the kinematics, or in the IK. And there was a numerical IK solver that's built into the DVRK. And I think Peter is partly, and Greg are to be thanked, which has worked really well. One of the things that we were surprised by was that it was possible to reformulate this using Piper's method, and actually come up with an analytic solution for the inverse kinematics. And that it's faster and was, as you can see here, significantly faster than the numerical solver in the last two lines. So on the at least 1 or 2 orders of magnitude faster. Now, that, then we started to do comparison. Now, here's the experiment. We had 9 volunteers who were not experts perform the peg transfer under teleop, and then 1 surgeon who is very experienced with the DVR, with the Da Vinci system. And then we have the robot. But what I mean just it's under full autonomous control. And the experiment was, we ran this for a number of trials. A trial is a full set of moving all the blocks to the right and then all the blocks back to the original pegs. And so the number here, you can see the number, each one of those is a sub-trial, if you will, a transfer. And so you can see the numbers here. The transfer time of the surgeon is significantly faster than that of the volunteers. But interestingly, the robot, when it's calibrated and optimized, is actually on par with the surgeon. And the success rate is also interesting on the right. Once we were able to introduce the calibration, the success rate went dramatically up. Now here's just a view of this being done in a bilateral mode. That's with activating both of the end effectors simultaneously. This is actually somewhat difficult for a human to coordinate 2 different end effectors in parallel like this. So, but no problem for the robot because each of those are completely independent processes, and we just take care that they don't collide with each other. And for the 2-arm case, we're actually able to do this faster than the surgeon, as you can see here. Faster than the surgeon, but also at the ever so slightly higher success rate. And what we mean by that is the robot, the human surgeon dropped 3 of them. Our system, the robot didn't drop any. Again, you see that these success rates are fairly high in all cases. That's promising, but it's a matter of how does the speed, what is the trade-off between speed and accuracy? So this was very nice. The last thing we've looked at here is actually the handoff. And this is particularly challenging because now you're depending on the accuracy of both grippers, the precision of both tools, because you have to perform this handoff. So we didn't have high hopes for this, but it was actually very successful. And again, Minho's engineering is really at the core of this. He was able to get the success rate up to 100%, and it's out of 120 trials, just every single one working. And the transfer time is actually slightly faster than the human surgeon. So this is actually very, very illustrative. It shows the motion of just a typical trajectory, and you see the volunteers are fairly, there's a lot of noise and their motions. The surgeon has much less noise, and the robot has very little, right? Because we're optimizing those curves. And it's in the bottom. What's interesting here, I'll just go through this really quickly, but in the bottom chart, what you're getting is the first one is in success rate, and so they're all very successful, all 3. In the handover, the second plot is the distance traveled. So the robot is shown in blue, by the way. So the robot is slightly faster, slightly lower distance. The number of collisions is shown in the third plot, whisker plot, and you can see it's very low for the robot. And then the last one is really interesting, is completion times. And so the robot is slightly better than the surgeon, and also almost 0 variance. So it's very consistent. Every single transfer is very consistently performed. And anyway, this was picked up by New York Times, a nice article on it. It was a little snarky, of course, being the New York Times, but anyway. So let's move on to needle transfer, and this is brand new. This is building on we've been working with the DVRK for many years now, and we worked on needles.
The system uses robust point-set registration.
Sorry, I was skipped that, but basically the idea is that we've tried to track needles to perform some suturing, and if you watch carefully, what's going on is that the needle has been painted with a yellow paint to make it visible to the camera. And we were able to get some successful transfers. As you can see, this is very slow. This has been sped up by 4 times, and the handoffs are very awkward, and it doesn't work. This didn't work very particularly well. We had a lot of problems with this essentially being able to hand the needle to be able to acquire the needle once it's punctured the tissue. So so this leads us to this new result that we call the Houston problem, slightly named after the Apollo 13 Houston, we have a problem, famous line. Here our problem is it's the handover of unmodified surgical tool obstructed needles. And particularly what we're trying to do is be able to study the problem of handoff or handover where the needles are unmodified. So here's a, everyone I think here is familiar with that problem, and it's very essential in suturing. And I also want to give a shout out to Mike Yip. I don't know if any of his students are here today, but they've been doing some really interesting work in this direction also. They had a paper this spring on handoff, and I want to recommend it. It was in ICRA or RSS, but it's a really nice result. And note that they do also paint the needle. Now, I also want to give credit. Mike and his students are working in parallel, independently, although we do collaborate, but he's also looking at unpainted needles. Okay, so here's the challenge. We want to be able to hand a needle off between the two end effectors. And what we do here is we have 3 cameras and a stereo pair and an overhead camera just because of occlusions. And as you can see, there's different poses, but some of them are harder than others. So the one on the far right is very difficult to model because of the needle is end on, and so you can't really see its 3D structure. So what we did was active sensing. So what we do is rather than just if we can't build a good model of the needle, we actually continue to move the needle until we can detect a reliable pose, and that is by being able to fit a circular arc to the needle. And then we also introduced an idea of a fine-grained grasping policy that once we understand the needle's pose, we set the needle up for the second gripper, and then we have a servo that is able to a learned control module that is able to then perform the grasp, and that's what's shown here. We can go into more details. I'm going to see that I'm getting short on time, but here's the idea is that we did a handover from one end effector to the other. The success rate, as you can see, is very high. And the completion time is fairly reasonable. What I want to say is that it also was able to generalize to new needles it hadn't seen before. That was surprising to us. That the generalization was fairly good. These are needles, as you can see on the right, that at least the inner 2 that are quite different than the training needle. And then this is the big, what we're most excited about is the multiple handovers. So the challenge I asked the students to see if they could continue to hand over the needle back and forth. And I expected they'd be able to get maybe 3, 4, 5 handovers before the needle was dropped. But to my very pleasant surprise, they were able to get up to 50 or more handovers before the needle is dropped. And so you can see at the bottom here, the 50s here, 50, 50, 50, 20. I think that was not out of 50, but these are very, very good results. And so we're really pleased with this, and this is sped up 15 times, of course, so there's a lot more to do, but it's promising that we're able to detect the needle pose, resolve it, and then actually servo the two end effectors to be able to hand it over in that way. Okay, so that's what I have, and happy to take questions. I also want to invite Brijan and Daniel to jump in as well. Thank you.
Thanks for a great talk. Sure there'll be questions. Okay, down at the end there.
Sorry if I guess you covered this and I missed it. Once you learn the algorithm using the fiducials and the RGB camera, are you still using the RGB camera without those fiducials to determine position, or is it purely based off the encoders?
Good question. No, after we do the calibration, then we take off the fiducials, so we don't use those at all. But we are still using the RGBD camera to determine the position of the blocks and the pegs.
Questions? Go ahead, and I guess Farshid, if you want to set up for the next talk. Yes.
Hi, Dr. Goldberg. So I just want to ask a general question. So what do you think for the Da Vinci robot? What are some other surgical tasks that you think we can potentially apply deep learning to? Because I'm working on Da Vinci and learning-based method too. I'm just interested in like, well, what do you think are some direction or some tasks for the Da Vinci that would be we can potentially apply learning method like very effectively to? Yeah.
Great question. So I think that I'm very excited because I think that this calibration procedure, the inverse kinematics, opens the door to lots of new tasks. And by the way, we're very happy to share this information. It's online. Both the calibration code and the inverse kinematics are available online. I also want to say that Minho and Brijan and Daniel are all very willing to advise, or we're all willing to share this with the community, just as we have benefited from the incredible generosity of Peter and Greg and others, and Intuitive. I think that we can start to look at tasks like suturing again. We're looking into that right now, and I think that there's many others. Resection. We could look at particularly, procedures like being able to extract a tumor and then sew, a suturing, sew it back up. I think that all of this, I should say, is really important, that it will have to be supervised by a surgeon, and this opens up lots of interesting questions about the user interface. And that I think that's going to be a big challenge. We need to bring in HRI experts who understand how do we make this trade-off, how do we make it intuitive and comfortable for surgeons so that they can be observing during these during the autonomous sections of the surgery, but are not burdened overly. And that's both during the learning phase and during execution phase. So that's something else we've been interested in looking at. But I'm very interested in hearing from the rest of you and the community on what other new tasks that you're interested in and are pursuing, because I think this is a major, essentially a team effort. And I really, again, want to thank all members of this community for their collaboration.
Thank you.
Okay, I'll just do a quick follow-up. Sorry, we're running a few minutes late, but when you want to do things like suturing, then you'll be sort of in contact with tissue applying forces, and your calibration so far, I guess, was done in free space. So, and I don't know if you can really attach those fiducials as easily while you're doing things in contact, but I'm just wondering if you have any plans to look at trying to also correct for compliance of the robot in addition to sort of kinematic inaccuracy.
That's a great question, and we haven't. You're right. Everything's been done somewhat in free space. I don't think there is much of a what you're suggesting is to be a quite a bit of change when they're making contact. And I think if the forces are low, that shouldn't be a problem. But as you get into higher forces, as probably is necessary for needle insertion, then yes, we're going to have to deal with that. And again, we want to stay away from fiducials during the actual surgery. So, but you're right. That's going to be something else we have to be very careful and look at.
thanks again. Thanks very much to you and your colleagues.
Thank you all.
All right, so the next speaker is Farshid Alambeigi from University of Texas at Austin. Just share your screen.
We have to use Zoom for
The
Blue Jeans.
all right, we see your camera now.
Yeah, the camera is on. I hit share screen for some.
You have to allow it.
Yeah,
Okay.
this.
Try that, but I hope, I mean, let's try, maybe if you turn off your camera, that'll make it a little less confusing what's going on here. Even though it's not working.
Let me join again.
Okay. All right. If you want, in the meantime, you can copy it and I can start transferring it to my laptop.
Yes, that's awesome.
Oh, that looks better. So you have to click up there, unless you want to do your own, that's just that.
I think something went wrong.
Yeah.
Let's see, it's working.
Yeah.
Fine.
All right.
I have a delay here, but finally managed to do it. Okay, cool. Hello, everyone. I'm Farshid Alambeigi. I'm an assistant professor in the University of Texas at Austin. So today I'm going to present part of my work that I did during my PhD in Johns Hopkins, and the rest is like a little bit of work during pandemic that we did in the University of Texas. So I wanted to, in the beginning, appreciate the NIH for supporting my PhD and then internal funds of UT Austin. So I want to hijack this symposium and introduce Texas Robotics. So this concept of Texas Robotics started 2-3 years ago. So we, like 4 different departments, EC, CS, mechanical, and aerospace, joined together. Now we have a relatively nice place in 16 core faculties and more than 40 affiliated faculties through the university working on different aspects of robotics, and we have more than 155 students. So we have 2 core directions in Texas Robotics. One is the general purpose autonomy or long-term autonomy on mobile robots and different aspects, even like robotic surgery and human-robot interaction from rehabilitation and surgical robotics. So they gave us like a very old gym that we had in UT. It's pretty large like space. So we have more than like 16 different groups working in this like large environment, from mobile robots to rehab robots, exoskeleton, surgical robots. So we have different, pretty much covering different aspects of robotics in our space. So getting back to the talk. I want to start with this nice plot that we have here. I took it from a paper. It's relatively old, like 2012, but they have this nice plot showing different milestones in basically surgical robotics. It starts basically from open surgery, minimal invasive surgery, robotic surgery, pretty much, I guess, all of you know these like backgrounds. I just want to focus on the last part of this graph. So basically, transluminal surgeries or the natural orifice transluminal surgeries. And in this paper, they call it flexible access surgery, but in the community, we call it soft robots, continuum robots, or robots that you want to import through basically small incisions, and they are flexible. So basically, give us dexterity in a small environment. But what is nice with these robots and related to these talks is that these robots are deformable. So you can call them deformable objects. Another thing that I added to this plot is surgical autonomy. So to me, the next milestones, these two basically part of the plot are the milestones that we need to overcome through the next years. So surgical autonomy, you can see on top right. So that's basically Robotic, like Peter is here. So that's 1992. They did it perfectly with Robotic. They did, I guess, total knee, right, Peter? So
Total hip first.
Total hip first. So perfectly, you see here, this is what surgeons are doing in the OR without the robot, and you see here perfectly, you can command the robot like machining and cut a bone. Why you can do it? Because it's a hard tissue, right? So you can pre-plan and then like machining, command your robot, go and cut. But what is challenging here, how about if you're dealing with a deformable tissue, right? So it's not possible because you don't know how the robot deforms, what's the property of that deformable tissue, and then comes to the focus of my talk today. If you want to do surgical autonomy on continuum robots, soft robots, and like flexible tissues, what should we do? Can we do modeling prior and then try to use some algorithms or do something towards surgical autonomy? So this is the plot that I made during my PhD. So focusing mainly on dexterity and autonomy, the last two milestones. X-axis is dexterity, Y-axis is autonomy, and then I have 4 quadrants here. So this is the space of all surgeries to me. Top left is like hard tissue related orthopedics neurosurgery. You are dealing with a hard tissue. If it's a hard tissue, as I said, in terms of autonomy, we are good because we can plan, we can just cut with the robot. But in terms of dexterity, we are not dexterous because first question comes if you're using a flexible robot or instrument. On a hard tissue, question is that can we transfer the torque? Does it buckle, does it break or not? So with respect to hard tissues, we are bad in terms of dexterity. On the other hand, on the bottom right quadrant, we have soft tissue related basically surgeries. And you know, we have a robot like Intuitive has, like that product is out there. We have concentric tube robot. I say we are really good in terms of dexterity, in terms of making robots that can flex and bend for many years. But what is hard here in terms of dexterity? Autonomy. Because these robots are deformable. And if you cannot model how much force are going on them and then basically how they deform, it's pretty challenging to do surgical autonomy with this type of robot. And in this quadrant is just basically traditional low autonomy, low dexterity. So what we can do actually, and what's the basically perspective of my lab is, the best ideal quadrant is top right? Basically we have highly dexterous robots and highly dexterous, or basically having algorithms, intelligent algorithms that we can do, basically bring autonomy in different sorts of basically surgery. So I just want to today focus on autonomy, having algorithms that we can work on deformable tissues and deformable robots. But the other thing that we do in my lab is developing actually innovative design, developing tools, flexible robots, and even implants that we can actually bring orthopedic surgeries to the right quadrant. So with this background, I want to start with the first part of my talk, which is, can we have basically algorithms that we do basically bring autonomy in surgery? Previous talk, Ken talked about actually his nice robot, his nice algorithms with EBRK, but as Peter mentioned, so I think he is not considering the formation of the tissues, even the needle, right? We know that if you have contact, we might experience deformation, and it brings a lot of challenges. So as I said, once we are dealing with rigid objects, so we can do pre-planning. How about if you are dealing with using DVRK to do basically manipulation on deformable tissues. You see here, it's like almost impossible. You can predict how it's going to happen to that tissue because it depends on the type of surgeon or the tissue or how you are grasping or manipulating. So to address this tissue, like you see, there are like abundant like literature. If you want to go and check from model-based, like from needle insertion, which is a deformable robot or deformable, let's say, instrument inserted into a deformable object. So here you have two deformable objects, I call it. So I should say, when I say object, it can be a tissue, it can be a robot. Or you can see here from model-based to find around the element analysis approaches to machine learning approaches. We can find a lot in the literature. But what I did during my PhD, and we are continuing with Munawar actually sitting here in my lab, is we wanted to look for data-driven approaches, but data, once I call it data-driven, it's not machine learning. So we say if you can find some like analytical approaches, that if we know the input and output, that we are basically input means that if I have a robot manipulate the tissue, if I have some information I can measure, can I find the mapping between this input and output and somehow estimate locally and online with a good speed that deformation and simultaneously use it for basically manipulation. So the whole idea is here. So during my talk, when I say I use DaVinci, I'll show you. We assume that here we have a camera. That camera can track some fiducials. And then we know the inputs coming from the robot. So the core of the idea is basically this part of the algorithm. We say, and if you look at here, this function, what it says. It says, let's assume we have an unknown nonlinear mapping between the inputs that we are giving to the soft object or the formal object, and we can measure some basically outputs. So if it's a smooth, so I say I can derivate, I can simplify or linearize that model and represent the relation between the input and output simply with an unknown Jacobian. So JC here representing the deformation of that object basically locally, and it can change. So with this definition, so we have a key part of this algorithm. If you check here, I say, if I know input, if I know output, if I can estimate that Jacobian, then I can put it in my control algorithm, which is simply a constraint linear optimization, and you can command your robot to do what you want, and then you can measure with your model here with delta Z what happens, and iteratively learn the deformation. So the key here is that we can start with some metrics, assuming that that's the deformation of my tissue, and then basically iteratively learn the deformation. But what we are using, that I said, we call it data-driven approach, is a simple Breuil update rule. So first rank Breuil update rule, you can basically Google that. You will see this nice approach is the result of an optimization that minimizes the two norm of a Frobenius norm of basically a function, and it says it's some assumptions. If you are near the final answer, you can estimate basically a matrix that relates the input and output. So this algorithm is the core of my talk today. So I'm using this for all the videos. So I'm going to show you some experiments that we did. This is actually, I'm using that basically algorithm. I challenged my lab mate like Shahriar, so to compare with the algorithm, like to basically see which one is doing best. But the key here I'm putting here is that the algorithm somehow works like human. So if I give you an unknown deformable object in your head, what you do is start manipulating. So in your head, map that deformation and try to understand. So if you look at the right side, the robot does somehow the same. So it tries to poke in different direction, learns the Jacobian, and then you will see, I will show you with some data, converges to the basically to the results that we want. And in all, I forgot to say, experiments, we are trying to move the green points to the red points, even that we don't know the deformations of the object that we have in hand. So we did like a lot of experiments, like basically in Hopkins, with my teammates of Jory Wang. He was a visitor student from Chinese University of Hong Kong. So we did all these works, actually was with his side. First time we presented, we got the Best Innovation Prize in Hamden. And I'm going to show you these videos that what we did with this algorithm. Very first thing that we did was, so we have different types of deformable objects. We call it here homogeneous. Basically, it was a piece of silicon we molded. And there is no heterogeneity in terms of mass distribution and then the elasticity. And we did different things. You see, if I go back here, so we did unimanual, bimanual manipulation, and then the goal always here was to move one point, the green point to the red point. Here we did also the constraint, basically manipulation, meaning that in the image space, we were forcing the robot to move the green point to the red point. Next step, we said that's easy, let's just make it more challenging. So we got this bottle, we partially filled it with beans and then that like balls. So the challenge was that as soon as you move the tissue, the beans are moving, so make it highly stochastic. And you never can model side things. And the goal was, can we do the same thing? And I want to get your attention to these plots. So one of them is the trajectory of the movements of the points in the space. And the other two, if you see this one, the second one is the error of the convergence from green to red. And the other one is that the manipulability measure. So we were plotting the Jacobian that we are estimating, and that has very nice information to us. We also said, okay, during manipulation, if I disturb it, if I cut the object, you see the mass coming out and then makes it more challenging. Can we do it? And we showed actually the algorithm is robust and can do that. The same concept, we said, let's do needle insertion. So needle insertion, typically, you manipulate the needle to go to the target, but here we said, how about manipulating basically the tissue toward the target? Can we do it? And once we are at the point, then insert basically to the target that we did also some ex vivo phantoms. I mean, the right one I really like because the robot is trying to move green to red, you see, and then I was trying to cut the tissue. The scissor wasn't sharp enough, but I said, let's just actively disturb the movement once the green is trying to go to the red. So why it's challenging? Because that Jacobian, I said, we are iteratively learning, and this is basically this tissue, as soon as you touch it, so deformation locally changes. So the algorithm should capture that basically change in the elasticity and deformation model, and we showed that actually it's working very nicely. I said the deformable object can be a tissue and a robot. So I want to change the gear now, go back to another interest of mine, which is continuum robots. The continuum robots are deformable objects. Since basically modeling the deformation is very hard, specifically in like once we are interacting with the environment, we have external forces, so it's very hard, and we can do mostly teleoperation. Basically, we rely on the human intuition to compensate for that difference during the control. Then I raised this question, if you want to do surgical autonomy with a continuum robot, can we do that or not? So then we tried it. So similar things like the literature, you see there are like different approaches here, and then we said, let's try with the same concept of the deformable object, the same algorithm. Here, we are imagining we have a deformable robot. We can measure some points, like basically the shape or one point along the shape, and try to control the robot to basically the same algorithm. I want to just skip this. So we tried, we have two different continuum robots or flexible robots, we call it. The left one is 5 millimeter Iwaki forceps, like a wristed, and the other one is like a 3 millimeter continuum robot that my colleague Stuart Comer actually made it in Hopkins. So we integrated with the EVRK. The challenge here was, if I don't know the deformation of this robot, and if I have backlash friction, these are tendon-driven robots, can I control that without knowing the deformation? Pretty much the same thing. We tried free bending, and you will see later on the more challenging cases. If you have interaction in the environment, still we can reliably control. And you see this like tree. We did all these experiments to show we can do from shape control to basically position control. I want to show you these basically interaction experiments in which the robot is interacting with an object in the environment that is not aware of, and the stiffness is also unknown. So I wanted to actually get your attention to these plots, to the Jacobian, that it's basically a representation of the learning. If the environment is flexible or deforming, the rate of learning is changing and the frequency actually is different. So this was a flexible foam or flexible silicon, and you see on the right side, if it's learning, this faster means that the rate of changes of the interaction is changing, and then still it can basically deform. And the most challenging one, so this was again a concave, like basically ball that tested. And look at that basic estimation, still fast but can capture. And the last one was the challenging one. It's just you find these in Amazon packages, right? The challenge is that if you push up to some points, they get very, like basically the air is trapped inside, becomes stiff. Before that is soft. So makes it very hard to estimate, but it was flexible too. So coming back to the point, if you want to do autonomy, surgical autonomy, manipulating a deformable object with a deformable robot. Now here, we don't know the deformation of the object, we don't know the deformation of the robot. Still, we see the deformation can be estimated and then controlled. So I'm going to skip this. So the same basically sort of experiments we did published in ICRA. So even if so this was like homogeneous objects. So the other one, bottom right, I'm showing that after this, if you cut basically during manipulation the object, so the deformation is totally changed. So the algorithm should be able to capture that, and we'll see it's pretty much it can do that. So this is the last thing. We did recently with my colleague on concentric tube robots in basically, to control concentric tube robots, as you know, if you are familiar with it, mostly we do model-based control. So you use constructor theory, and then to control that, you derivate, find the Jacobian, model-based Jacobian, and try to mostly teleoperate. And almost, I say, 100% of or 90% of the literature is prevented. Because if you have forces, everything is changing. What we suggested here, we called it hybrid dual Jacobian approach, based on the basically Breuilian optic rule that I was talking to. So one big issue with that data-driven approach with the Breuilian is, I told you, so the initialization of the algorithm is the key. If it's not, if you just pick some random matrix, it might take like forever to get to where you want, makes it very slow. Obviously, if you are dealing with a robot, you don't want to wait forever or even like. So then we said, how about combining data-driven with an analytical approach? So I have a model, I know that. So the change, if I'm interacting with the environment, should be in the neighborhood of that modeling approach. So we said we don't want to trash what we know from modeling. Let's use it as an initialization here and then combine it with this data-driven approach. So this JM is the model, and this JD is coming from the Breuilian update rule. And here is what we suggested. We called it like hybrid dual Jacobian. If you check here, then we have two terms here. And the initialization of JH here, it depends on the JM. And we have a switch term over there that over time, so in the beginning, instead of starting with random matrix for Jacobian, we say let's start with that model-based Jacobian. And then through the time, these two terms are the weights that we are giving to our initialization of the data. This means that the matrix that we start is model-based, and then we use that matrix to initialize our data-driven approach. And here is the basically, and then with this, we can use pretty much like the Jacobian pseudo-inverse of the Jacobian control. We did this in simulation. We are working actually on the experimental aspect of that, but I want to show you what are the differences between different modes here. If we use pure data-driven, pure basically hybrid, or the model-based. And we did different simulations. So left side is pure data-driven Breuilian, and we asked the robot to follow a rectangle. So it's a challenging task. You see the Breuilian update rule just becomes very unstable because it cannot like quickly converge to the result. On the middle is the model-based, so we know that it's working, but at some point it's not accurate. So you see it's trying to follow the basically rectangle, but if the error, the red is the trajectory that the robot goes. But look at the hybrid one, so the last column. So we are mixing and we are using hybrid dual Jacobian, and it compensates very nicely. So that was free bending motion. Now we said, if I add some external forces, point load and then distributed, and we compared model-based with the hybrid. You see, similarly, if you have external load with model-based, as we expected, we diverge, but still with the basically that hybrid approach, we can compensate that and work. And we did also the manipulation. If we have like a deformable tissue, we just made like with basically a mass spring damper model. Robot interacting. So again, nicely, we are showing, of course, this is simulation, but we can compensate that difference. And you see model base, it gets as expected unstable because you have external loads coming on the very flexible robot. They are like a spring and start to vibrate. So this was, I guess, the last slide of basically my talk. Just wanted to wrap up with the things that data-driven approaches, once we call, is not like just refer to machine learning or artificial intelligence. We have nice inverse models that we can use, and there is like a theory behind those. And we can basically somehow know what's happening. Machine learning, I guess, combination of machine learning with approaches would be the best approach to deal with these. And thanks so much for the attention.
Questions? Sure. Yes.
I just have a question about when you learned the Jacobian for the object, the deformable object. Was it like an online learning process, or you did learn it offline and you adaptively?
But the key point here was that we use iterative learning. We say, I move or manipulate the tissue and I can measure. So at each time, actually, whatever video that I showed you, everything was online. But the key is that we are iteratively learning, and all our learning depends on the history that we have. So that Freudian operator we are using has two terms. The first term is the previous learned Jacobian adds up by a change to that matrix. So, and everything is basically online, and then we are showing that it's actually can capture very quickly the deformity.
Questions, either from the audience or online? That's a nice talk. I wanted to actually ask one question on the. I'm interested on the cutting, because yes, it adapts, but does it adapt quickly enough? Because a lot of times when surgeons are doing tasks, they're, let's say, manipulating and cutting at the same time. So you need to have a very fast update, and they probably have some they have prior knowledge. They know they're cutting it.
Exactly.
And so I don't know. At first, do you think your method will adapt quickly enough? And if not, do you think of a way of maybe injecting some sort of prior knowledge or more information?
So the videos that I showed you, I want to refer to that actually ex vivo phantom. So that was real time. We didn't increase the speed. Why? We're disturbing. So if it's not happening, even if it's happening very fast, you see a sharp change in the Jacobian learning, because so it's all about input and output. So if it's changing, so you see that sharp change, and then it comes to the basically convergence after learning. I say if the rate of, depends on the tissue, I say. So if it's just like something that the rate of change is not that fast, yes, we can do that. But obviously some like prior knowledge, physics-based knowledge helps. Like the case of, I think the extreme case is concentric tube robots, right? Because they are flexible. I mean, this new model, if we have some prior knowledge, it helps, right? We say, here is the model. So the neighborhood can be the change. It's like a covariance that we have on Kalman filter, right? Obviously, prior knowledge helps to converge like much faster.
All right, thank you.
Thanks so much.
Thanks, Farshid.
Great.
Go back to your workshop now.
Yes, yeah. Okay.
Doing double duty. So now we're going to kind of head into the AMBF sort of simulation tutorial, but we're going to start off with just some presentations. So I guess, Farid, you're speaking next, right? Yes. We'll have Farid, Sagar, then Adnan, and then it'll be coffee break in the tutorial.
Can I share my screen? Should I connect?
Yeah, if you want to connect that, also share your screen, that should work fine.
I think either way is good.
You all set? I mean,
so should I click on share?
Yeah, click on share here so the people online can see it. That one there. Yeah, that's fine.
Hello everybody, my name is Farid and I'm presenting the surgical simulators to support machine learning. I'm part of the AIM lab, or Automation and Interventional Medicine Laboratory from WPI, and I'm a PhD candidate. So wants to have access to my computer, I will give access, okay. So healthcare robotics research teams, the themes in our lab are as follows. So we do have basically two main teams. The first team is the surgical theme works, which are consisted of the DVRK type of work. We have MRI compatible robots, which are the neuro robot and also the prostate biopsy robot. And we do have some assistive robotics works, which are hand exoskeleton, lower limb exoskeleton, which are rehabilitative robots, where people have had strokes from before, and then it helps them to regain some mobility back. And also we have PAVI, of course, it's a autism robot. Children with autism to kind of learn better by interacting with a robotic type of a toy. So in the past, I would say 20 years or so, a lot of companies, starting from Intuitive and giving way to other companies like Auris, Monarch Platform, Diffuse System, and also like ROSA, which is a neurosurgery robot. A lot of these companies have emerged. And what is, ideally what we are aiming for is to have a common framework that can we implement the learned models that we have trained to any of these systems without having to do any extra work. I jumped. Right? Okay. So what we have right now is a DVRK platform and Raven platform. For the DVRK platform, it's a common hardware system as well as a software system using the SIS library that we can actually train models. We can have data collected from these robots, as well as we have different simulators, including the Gazebo, RViz, and also the AMBF, to basically train our models there. So what would be nice for us to have is to have a common API, where all the researchers in the field, they can use to train models, collect the data, and then share it with the community. So this brings me to the CRTK, which is the Collaborative Robotics Toolkit, which basically enables us to collect the data, share it with a wide community of researchers that are using the different robots. They can have different input devices, and they can also have output devices. But this CRTK, it enables them to have a common grammar, as you would say, to interact with these robots and collect these data for learning purposes. As you might know, the community right now is about 35 different universities and institutes using the DVRK systems, and about 15 institutes using the Raven systems. But there are many more universities that still are interested in this field, but they are limited by the lack of having access to the hardware. So this brings us to the need for having a simulation and simulator platform for learning different algorithms and models for the surgical tasks. Our team, in collaborations with Johns Hopkins and the University of Washington, we have developed the different platforms, simulation platforms, including the AMBF, as well as the different robot models for running on the Gazebo and RViz platforms. that can be used for achieving the tasks of reinforcement learning and machine learning in general. So our AMBF simulator, it has, Adnan will give a really more detailed overview of the system, but it's a asynchronous dynamics body simulator which enables reinforcement learning. The whole idea behind developing this simulator was for use in the reinforcement learning and for use specifically with the surgical robots. And this simulator has readily available robot models, including the PBRK system, Raven systems, and has KUKA LBR and also LBR Med in there. The whole architecture of this simulator enables us to have handles to different objects, including the world and the robot model. And also, the AMBF supports, as I mentioned earlier, the reinforcement learning toolkit, which in short, we call it ARL, which can interact with the objects within the simulator. You can run the simulator as a headless simulator, so we don't really need to rely on the graphical interfaces, but the model can, in the background, have a loop in training the model, interacting with the objects, and having access to the state-of-the-art reinforcement learning algorithms to train the model. The ARL uses the OpenAI gem as well as the baselines for the providing us with the algorithms, and then the simulator takes care of the rest of the interactions with the robot models. One of the good features of the AMBF is its throttling ability, which means that if the system has problems with communication delays or the simulation delays, the simulation can automatically throttle because it's an asynchronous simulator, and that can help with having the stable simulation. And then the workflow for the reinforcement learning model is that you can, so ARL provides you with the ability to configure and create your model and set your reinforcement learning parameters, and then you go to the training phase where the simulation platform interacts with your objects, uses the algorithms to train the model, and then after it's trained, you go to the training and to evaluation phase, and then finally you just deploy your model on the real robot and test it. Another feature that we have introduced to the AMBF is the dynamic server, where what it does is that basically you can feed it a robot description file, which is the ADF file, and then it automatically uses the description file to create a tree-like structure of the robot, and then uses ROS interfaces to give you all the dynamics parameters of that robot using the ROS calls, ROS service calls. So you would essentially have access to Jacobian information. You can implement different controllers, such as the inverse dynamics controllers, gravity compensation, and so on and so forth, using this server. And then another thing is that, okay, we have trained our model, we have a trained model, but how good is it actually? How do we evaluate it in real life? So we need to have a way to actually see how does it really interact with the humans and how humans, see this as whether it's a good feature or it's just like something that it's just a training for the sake of research. So we can use different MRI studies like fMRIs or the EEG sensors to see the brain activity and see if these semi-autonomous or collaborative models can help achieve specific tasks. So we go to the MRI-compatible robots in our lab, which are the biopsy robot and also the neuro robot. The neuro robot is a robot that uses the ultrasound probes for conformal ablation or controlled ablation of the cancer cells within the brain. And the prostate robot is a needle-guided robot that takes a biopsy of the prostate. using the guidance of the MRI. So we're going to take a look at how simulations can help us achieve these two tasks. Just to give a quick overview of how this conformal ablation transducers work is that we have a piezoelectric piece that's in a shape of different types of shapes. It can be circular, it can be a square shape, and then they are able to direct the heat pattern to a specific direction. We have, for example, 90 degrees, 180 degrees, so on, or 360 degrees. And then we can start rotating these probes once they are within the brain to have a conformal ablation of the cancer cell. So how we are doing simulations to create this base frame for how the acoustic pressure field is generated. We use console to create this acoustic pressure field and then feed the trained model as the base for the thermal propagation model. And after that, we can simulate this thermal propagation within the console. And then once we have this model trained, we can show that, okay, how does it work for the circular, how does it work for the directional one, and how does it work for the square-shaped piezo piece. And then we want to also cross-check it with how the real-life probe actually propagates heat. For that, we use a milk phantom, which is specifically designed in a way that it shows how the actual heat will propagate in a brain tissue. And then we start hitting the milk phantom and getting the MRTI data from the real MRTI data from the scanner. And we want to cross-check it with the learned model, which we can see it in this slide. So the simulation and the MRTI data is closely related to each other, which is a good sign. And then that's how we are basically having the probe rotated in both the simulation and the MRTI data. And that's how basically the heat is propagating, as well as we have a constant speed and rotating the probe, a 90-degree probe within the sample, which are closely following each other. Maybe covered this part. And then these are the ablation results, where we have gotten a really good result for both the simulation part and the MRTI data. And then what we did was that we used the simulation data from console as a ground zero for our reinforcement learning agent. And then we use the BRATS data set, which has a lot of cancer cells data for brain tumor images. And then we have created this margin of ablation, desired ablation, that is shown in red, and then feed it to the trained reinforcement learning model and to see how it sets the parameter for the speed of rotation. And here we can see the result. So in the left, we can see the pixels that are below the desired temperature in the dark blue. And once we start heating, these regions start heating up. And it is a little slow, so I'm just going to go forward. And then at the same time, the model is commanding the robot to rotate its probe. And then we are basically heating up all those desired pixels, starting in dark blue. And then the robot eventually achieves the full ablation. And these yellow pixels are the pixels that are over ablated, which means that it got more temperature than it needed to kill these cells. And then these are the results for the reinforcement learning model versus using a 360 probe. So the red is the cancerous region, The blue region is where the desired ablation based on the reinforcement learning model was burned, and the almost, I think, brown region is where the region would be heated if we would use the 360 without rotation, 360 ablation probe instead of a directional 90-degree probe, which shows that we are basically preserving more healthy tissue than we would normally do when we would use just a 360 probe. What we have recently opened up in WPI is a center called Practice Point, which is a membership facility for developing surgical robots and instruments. This center provides every aspect of the development cycle, from the design all the way to the testing and production. Not production, I mean production of concepts to be exact. So we have MRI machine, we have CT scan machines, a fully functional OR room, as well as the 3D printing capabilities, laser cutting, machine shops, and the electrical rooms that enables you, and also motion capture labs to enable development of all sorts of rehabilitative as well as the surgical devices. And here's a quick pic of the MRI robot with Rick Fischer. And that's a happily patient going into the MRI board. Yes, thank you for listening.
All right, questions on the presentation? So I was wondering if I understood, you're using Console to do the analysis of the heat flow, but then
Yes.
you're using AMBF and reinforcement learning to figure out how to move the probe to get a desired shape? Is that?
Yes, so we need Console to give us a model of how the heat will propagate in general, and then we use a reinforcement learning model to know how much we should rotate in order to achieve a conformal ablation.
Okay, got it. All right. Questions? Well, thanks again. Yeah. So this will be the last talk before the coffee break. And then Munawar, Johns Hopkins, talk about AMBF 2.0. So yeah, we're going to need to, you're going to share your screen too, right?
Yes.
Yeah, we can do this so we can see it here. Getting an early cloud. Yeah. All right, so you haven't shared your screen yet, have you?
I'm just doing it now. Can you see it now?
Yes, yes.
Okay. Hi, everyone. I'm Adnan Munawar, postdoctoral fellow at the Lab for Computational Sensing and Robotics at Johns Hopkins. My advisors are Dr. Peter Kazantzidis, who is sitting over here, and Dr. Russ Taylor, who couldn't join us today. I'm going to be talking about AMBF, and specifically about AMBF 2.0, which we released this year. Before I begin, if you... Oh, sorry. Okay. So if you haven't already had the chance to set up AMBF, and if you would like to, you can either go to this website or scan this QR code. If you didn't get time to set up anything, if you only want to install Blender, which is I think step number 2, install that and you can follow those instructions. So you can skip all the rest of the tutorials and you can just walk with me for that part of the tutorial. The surgical simulators. Well, surgical simulators are useful because they allow rapid prototyping of design ideas, kinematic and dynamic testing of different robot designs, rapid implementation and analysis of force controllers, user skill training and benchmarking, and last but not the least, a very cost-effective way of training machine learning algorithms. The video is from 2017. We were just having some fun with the Da Vinci and brought an instrument or two. So another reason to have simulators with case to break the real robot in the lab. Gazebo and Univ are arguably the two most popular community simulators out there. There are other simulators such as Mojoko and Unity, and Unity is not necessarily a simulator, but these are still most commonly used by the community. Both of these simulators employ a tree-based hierarchy for describing the robot, as well as for describing their scene graph. You can see the tree-based hierarchy on the right with a base link at the top, and then all the other links are connected to the previous link, so each link can have a maximum of 1/3. While this tree-based hierarchy makes sense for serial robots and for the scene graph, it creates big problems for simulating surgical robots. Why? Because surgical robots often have kinematic loops, and that's how you get a constrained actuation. Other than that, these simulators lack software support. These simulators have a retrofitted communication interface and many drawbacks, but I don't want to take away anything from these simulators as they are much bigger and better than AMBF in almost everything has to do. But I might be picking at them a little bit throughout this presentation with no hard feelings. So a good example of a surgical robot is shown on this slide. This robot is the WPI's neurosurgery robot for deep brain stimulation. The base of that robot has a 6-bar linkage, and the top has 2 interconnected 4-bar linkages. So you cannot conceive a tree for this kind of robot. You will have these loops, and then you will have to test those loops. To design this robot in Gazebo, for instance, you will have to develop an XML-based SDF description file. You will then also have to work around the tree-based hierarchy. And doing so, you will be faced with a very tedious, error-prone, and redundant design process. Not to mention that you're working in XML. Let's say you got over that process and you made this robot and you simulated this in Gazebo. You'll have to still do a lot more work to just control this robot using ROS or an external node, which is unnecessary. In addition to these limitations in simulating surgical robots, both VREP and Gazebo do not support soft body simulations. Other simulators do to some extent. Neither of these two simulators have support for input devices out of the box. You could add input devices later on, but they don't have any special kind of support for haptic feedback. And more importantly, all the cool features that you want to get out of this robot is to control this through ROS or external nodes. Those packages are retrofitted. Neither Gazebo or VREP was designed to incorporate those packages, so they're just like an afterthought, and which makes the process of building on the simulators really hard, especially if you have an iterative design process in which the robot continues. After years of trying to simulate the Da Vinci surgical robots and writing plugins that were depreciated with evolving APIs, the idea of a novel simulation framework was conceived, and AMBF is just a realization of that idea. AMBF is robust, and it involves a lot of individual components that together streamline and simplify surgical robot simulation. The tiles that you see on the right are just some of the components. The ones in purple are components that allow external robots to be simulated in AMBF, whereas the tiles on the right, the green and all the other colors on the right side, are mechanisms for getting data out of AMBF for ROS-based nodes or for haptic device drivers. Incorporating input devices is important for surgical simulators because in surgical simulators, we need these input devices to teleoperate robots and interact with the environment. The physics loop is computationally very expensive. The collision part is. adding a high-speed communication device with this loop is challenging. Adding multiple devices with variable communication frequencies is just unfeasible. AMBF was designed from its start to include input devices in an asynchronous manner. As you can see in the video, we have 5 different hands or 5 different devices interacting with the simulation. 3 of them have haptic feedback. And if you see the 2 graphs on the bottom, the one on the left is the frequency of the physics loop, which is destined to run at a kilohertz, and it suffers based on what collision we are currently in. But the device update almost stays at a kilohertz. So this is really good. This means that we can add different operators to do different tasks in a simulation environment. What really drives AMBF is a novel description format, which is aptly called the AMBF description format. Unlike Gazebo or URDF, which use XML, or Mujoko for that matter, we use the very humanly friendly YAML format. And you can just see from this style over here that just by looking at it, you can understand different attributes of the robot. There are no angle brackets or closing slashes, so your program wouldn't fail if you forgot to close a certain data block. To support kinematically returning robots, the ADF also does not enforce any hierarchy. So you can really have joins and links in any order, and AMBF will internally create this deep hierarchy when loading the AMBF description file. And it will check for loops and different pathways to different children. And what it will essentially give you is that every body that's higher up in the chain will have access to all the lower pairs. So by getting a handle to a base body, you can control all the joints. And that's very useful when you're trying to control the robot through an external node, and you only want to control up to a certain joint, and then take the handle of the body afterwards, and then control all the joints in order. And we use that a lot. And even though AMBF is very simple and very user-friendly to read, it's still another format to learn. So we have created the Blender AMBF add-on so that you don't have to touch a line of the description format and use the GUI 100% to make very complicated environments. And there's a hands-on session for the Blender AMBF add-on later today. And we, based on, to the best of our knowledge, the Blender AMBF add-on is the most feature-rich and advanced tool for making robots and environments for AMBF. Quick history and roadmap of AMBF. You can see it's a very baby project compared to Gazebo or VREP. It was released in 2019, or the first release was in 2019 at least. In 2020, I moved to Hopkins. We had some interesting projects, and we required adding support for textures, shaders, and vehicles to AMBF. So we released 1.2 in 2020. We just released 2.0, which is light years ahead of what we had before, but it's also still very familiar and very similar, such that all the previous features are still supported, so there's no backward compatibility. And then in the future, we have a bunch of different plans, but that's not important for now. One of the primary reasons for working on AMBF 2.0 was to incorporate simulation in the loop. What this means is that you are doing an actual surgical procedure and you would want a replica of the procedure in the simulation, and you can add things like guidance or forbidden region virtual pictures. To do so, you really need a very fast update rate. Previously, if you were to use this, to implement this kind of intelligence in AMBF and connect a real robot, you would have to use the communication, the server-client model to do so. And that had its communication overheads. Because you were using ROS as a middleware, you had the data serialization, deserialization, and all the communication overheads, which is not really ideal. So we really wanted a way inside AMBF to neglect all of that. And that's where we made a plugin interface. And we did a whole lot more along with a plugin interface. And last but not the least, we cleaned up AMBF so that you can take all the data for different bodies and environment and use it for external applications such as the rigid body dynamics library, or use it for any other purpose. In a nutshell, these are the key features of AMBF 2.0 compared to 1.0. We have a completely redesigned core. It's faster, it's better. It supports dynamic parenting, so you can have a description file loaded afterwards that has a parent earlier, or you have a parent earlier and its child is loaded later, so you can mix and match however you want. It wouldn't matter. You can still parent to the right body. The scene graph is optimized, so even though AMBF was faster than Gazebo and Univ, this makes it even faster. The biggest update is a robust plugin interface. We have made the rendering pipeline modular so that you can generate things like segmentation index or superimpose the segmentation index on the depth pipeline. And last but not least, AMBF 2.0 has support for volumetric rendering and grid. A point I mentioned earlier about exporting AMBF data for outside applications, this is what we used to do before. We had an AMBF description file. This file will be thrown inside the framework library, and all the AMBF objects, which is, for this example, a rigid body or soft body, will pull out its relevant data, and then that's that. If you wanted to re-access this data, you either write a parser for AMBF, or you go look at those AMBF objects and have to deal with a lot of unnecessary information to get to what you need. This has been cleaned up with dynamic ADF loader, which checks for the version, and then it extracts all the elemental attributes. So the elemental attributes are the most basic attributes that cannot be subdivided. So these could include hierarchy, communication, visual, collision, and things like that. And then these attributes are paired together to form compound attributes such as a rigid body attribute or a soft body attribute, and so on and so forth. No change for the end user, but a big change for us, because we can now use a header-only file to give away AMBF data to all the external attributes. So if you have worked with OpenVR or OpenXR, it's kind of the same concept. We have made a very robust and hierarchical plugin interface. So if you look at the AMBF simulation scope, you have the AMBF simulator. If you look at the image on the left, the simulator has a single instance of world. The world will have multiple instances of models, and each model can have multiple bodies or sensors and actuators and so forth. Similarly, you have the plugin interface. At the highest level, you have a simulator plugin. It encapsulates a world plugin, which encapsulates a model plugin, which encapsulates multiple object plugins. So these all can be attached to their relevant objects on the left, and plugins are also loaded using the AMBF description file. On the right shows you the multi-model rendering pipeline. So we render the scene as usual on the leftmost figure. We generate the depth point cloud, and then we can use custom shaders to render the segmentation index and superimpose it on the depth point cloud and stream it out using ROS. With that, I would like to quickly go over some projects that we have been working on using AMBF. The first one is the most non-surgically related project. So the one thing that I want you to take away from this talk is that none of these examples are specialized. They all use the same AMBF description files. There is no source code modification. It's just AMBF is robust enough to give you these different by the same core in the same description format. And what you see here is a extra planetary environment in which you have two different rovers that can be controlled using a Xbox remote, and you can introduce teleoperation delays to mimic the real communication challenges that are faced when you're teleoperating different planets. And the goal here is to either pick up these blocks to build a bigger environment, or to go over to that black sort of pillar and then take out those screws out of those holes and then reassemble them together. So a bunch of different interesting applications. The second application is the volumetric drilling and running project. This project is in collaboration with a bunch of folks from Hopkins, and we are deploying this system at the Johns Hopkins Otolaryngology department so that residents and surgeons can train on the simulator and we can assess their skill. And then we can benchmark the skills of residents compared to trained surgeons. The pipeline is shown on the right. Again, no change to the India source code. You load your volumetric plugin through AMBF description file, and then you can have a plugin for actually removing this bone tissue that's seen here. And you can have another plugin for VR, as you can see here. So it's all very fast, it's all very modular, and it's all very robust. Another project is in collaboration with SICTEDS in Canada, and this is the simulation in the loop project that I was talking about earlier. We are using the DVRK to teleoperate a simulated PSM that's operating on a very dense skull. The collision of the PSM shaft is, it's not just a point on the tip, it's actually taking care of all the points behind the tip as well. And that simulated PSM is then controlling the actual PSM. And we want to take this project further so that we can register the simulated model with the real skull to do actual bone drawing. And since we're using plugins, there is very little latency, and this is being used in real time. And finally, we have the surgical robotics challenge. For those not familiar, this is the link where you can find this challenge. Again, there's no modification to the source code. AMBF will give you the state of all the objects, on cloud, the segmentation. And you can control the manipulators using either velocity control, effort control, or position control. And you have a bunch of different example scripts in there if you wanted to control these simulated robots using GeoMagic or Phantom or DVRK or any other input device for that. And with that, I would like to thank you all for listening to my talk. And I would like to acknowledge the following sponsors for enabling AMBF and this research. And I'll take any questions.
Space robotics simulation, how easy is it to change the gravity? And is there any friction models for the sand that you have?
The gravity is easy. You can change them by raw param, so you can set the world, or you can change that in the world description file. We have set it to, I think, 2 instead of 9.8, set it 2, but you can change it dynamically. In terms of the friction model, the sand is not displaceable, so it's a fixed ground, but you can easily change the friction of the tires and the ground. And it's a combination of those two that give you the traversal or that it's easy to change as well.
And the same with like maybe working with bone or tissue. Can you have some contact dynamics there? With
Of course, yeah. We'll go through the AMBF add-on and we'll discuss these kinds of things.
Yeah. So actually, following that question, I'm very interested in the compatibility of incorporating tissues and, let's say, elasticity. Because in the last example you showed, that was very impressive that you have the robe. I was curious, you know, the purple cloth there seems to be also soft-ish or deformable. Just curious.
Good point. So let me play this video again. It's not deformable, but it fools you well enough to make you think that it's deformable. So the thread is deformable, easy to see. The ping phantom is rigid. What is movable is these head markers. They have a 6D spring. So once you put your needle through, they can deform and give you this thing. AMBF does have soft body support, but the number of variables to tune are just too many. Having the plugin support is actually making the software simulation much easier because you don't have to worry about changing them through the ADF file and then send them once and forget about them. With a plugin, you can change them on the fly, create a ROS publisher so you can have a GUI to change those like Jan's modulus or like drawing like error resolution, those kinds of things, and see the behavior. That's in fact something that we want to try very soon, even with this project that I showed here. So I'm not shown here the scalp on top of the skull, but we intend to make a soft tissue of that scalp, so that when you put your tool, you can actually see it deforming and go through that. So yeah, that's something that we are hoping to get into very soon.
Awesome. Thank you.
It's just a small question. Is there? I see that this works with ROS1. Is there planned support in the future for ROS2?
Certainly, the way ROS is integrated into AMBF is a totally separate package that is not retrofitted. It was designed with AMBF, but it was designed to be replaced. So ideally, you could replace it with.
So it's kind of isolated in a specific part of the code.
Exactly.
And could you be.
Yeah. You can replace it with
ROS2 or even other frameworks.
For sure. Yeah.
All right. Well, thanks again. Take the coffee break in a few minutes. So it's the coffee break time, and then at 3:30 we pick up again with the hands-on part. So I'll just see you all back here.